Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, we are going to discuss an important topic. Let me write today's topic. Today's topic is virtual displacement. Let me write it neatly. Virtual displacement, principle of virtual work, and D. Ellenberg's principle. We will discuss these ideas today. So let me underline the topic. First, we will talk about virtual displacement, then the principle of virtual work, and then the important principle. This is pronounced as the Ellenberg's principle. First, what is virtual displacement? A virtual displacement is an infinitesimal displacement of a system. It refers to a change in the configuration of the system as the result of any arbitrary infinitesimal change of the coordinates of the particles of the system or parts of the system, consistent with the forces and constraints imposed on the system at the given instant of time t. Let me write it. This is worth writing. A virtual is infinitesimal displacement of a system is a change in the configuration of the system configuration of the system as the result of any arbitrary, let me set my pen, any arbitrary infinitesimal change of the coordinates, change of the coordinates, change of the coordinates. Let me add a page to this. Consistent with the forces and constraints imposed on the system at the given instant t. So let us understand this definition. Let me first check it. A virtual infinitesimal displacement of a system is a change in the configuration of the system as the result of any arbitrary infinitesimal change of the coordinates consistent with the forces and constraints imposed on the system at the given instant t. Let us understand it. First thing, virtual displacement is infinitesimal, right? And it refers to that change in the configuration of the system which results from any arbitrary infinitesimal change of the coordinates of the system. So if we have a system of particles, now there is a change, an infinitesimal change in its coordinates, right? That leads to a virtual displacement of the system. And important is that change, that displacement, that virtual displacement which takes place must be consistent with the forces and constraints imposed on the system at the given instant t. We denote it by delta Ri, and we write it in terms of Cartesian coordinates. So delta Ri here denotes the virtual displacement in some system in Cartesian coordinates, right? Now it is different from the actual displacement. You need to remember this. Actual displacement of the system occurs in a time interval dt. Actual displacement occurs in a time interval in a time interval dt. This is the difference. So actual displacement we must not confuse with the virtual displacement. Actual displacement occurs in a time interval dt, and during that time forces and constraints may be changing. But in case of virtual displacement of the system, there is no elapse of time. Virtual displacement occurs at a particular time t, at a given instant t, and that virtual displacement is consistent with the forces and constraints imposed on the system. That means during virtual displacement, forces acting on the system and constraints acting on the system cannot change, they are fixed, right? So let us move to the next thing. Suppose the system is in equilibrium. Let me use this color. Suppose we have some system of particles, for example. Suppose this system is in equilibrium. That means the total force on each particle in the system vanishes, or total force on each particle of the system is zero. So let me write that mathematically. If Fi is the force on ith particle of the system, then Fi is zero. This is the condition for equilibrium of the system. It is understood we are talking equilibrium in terms of translation, not in terms of rotation, right? Then we have to consider the torques on the system. Suppose the system is in equilibrium, that means the total force on each particle is zero. That means Fi is zero, where Fi is the force on ith particle in the system. Then clearly, if you take the dot product of this force with the virtual displacement, that dot product is also zero. Then Fi dot delta Ri is equal to zero, right? Now what is Fi dot delta Ri, where delta Ri is the virtual displacement of the system? This dot product is the virtual work of the force Fi. This is virtual work of the force Fi, right? So if my system is in equilibrium, that means total force on each particle is zero. That means Fi is zero, where Fi is the particle on force on ith particle, total force on ith particle. Then clearly the dot product Fi dot delta Ri, which is the virtual work of the force Fi, is also 0. So if we sum these products, these dot products over all particles, that sum must likewise be 0. That means, let me change the color of my pen. That simply means that I can write summation I Fi dot delta Ri is equal to 0. Let me name it equation first. So far it is all understood. What we have written, we have simply written the condition for equilibrium of a system in terms of the virtual work. We said if we have a system which is in equilibrium, then the total force on each particle must be 0. Then the virtual work on each particle must be 0. And then we summed over the virtual works over all particles in the system and equated that to 0. So this is simply what? It is the condition of equilibrium for a system of particles written in terms of the idea of virtual work. Now we can decompose this force because this Fi is the force, total force on the ith particle. This can be decomposed into two parts, applied force and the force of constraint. So let us do that in the next page. We decompose Fi, that is force on total force on the ith particle, into the applied force, which we write as Fi superscript A. It denotes the applied force on the ith particle, and the force of constraint, which we denote by small Fi. So capital Fi superscript A is the applied force on the ith particle, and small Fi is the force of constraint on the ith particle. So the total force Fi on the ith particle can be written as sum of these two forces, or it can be decomposed into these two terms, Fi superscript A plus small Fi. Let me name it equation second. So using equation second in first, what we get? Using equation second in first, we get, let me add page to this. I will get this summation I Fi applied dot delta Ri plus summation I small Fi dot delta Ri is equal to 0. This is my equation 3. Summation I fi apply dot delta ri plus summation I fi dot delta ri is 0. What we have done, we have simply substituted equation second in equation first. So we got this equation third. Now, the second term in this equation third, that is this sum. What is this? It is the net virtual work of the forces of constraint. It is net virtual work of the forces of constraint, right? Net virtual work of the forces of constraint on the system, and the first term is the net virtual work of the applied forces on the system, right? Now, if we put a condition that we have a system for which the net virtual work of the forces of constraint is 0. So if we set this condition that we have such a system in which the net virtual work of the forces of constraint is 0, then the condition for equilibrium of a system becomes, because one term will go, we will get summation I fi a dot delta ri is equal to 0. Let me encircle it and name it as equation 4. What is this? What it says? It says that if we have a system in which the net virtual work of the forces of constraint is 0, then equation 4 holds. Equation 4 says that the condition for equilibrium of a system is simply the virtual work of the applied forces vanishes. This equation 4, which is simply the condition for equilibrium of a system in which the net virtual work of the forces of constraint is 0, this equation 4 is the condition of equilibrium for that system. This equation 4 is called principle of virtual work. So it is a name. This is principle of virtual work. This principle of virtual work is simply the equilibrium condition for a system in terms of this virtual work, in which the net virtual work of the forces of constraint is 0. Now in this equation 4, the coefficients of delta Ri can no longer be set equal to 0, because in general Fia is not equal to 0, since delta Ri are not completely independent, but are connected by the constraints. These virtual displacements in the equation 4 are connected by the constraints, so they are not independent. So we cannot identically equate these Fi's to 0. For that, what we have to do in order to equate these Fi's, that is the coefficients of delta Ri's to 0, we have to transform this principle of virtual work into a form in which the virtual displacements are in terms of the generalizer coordinates qi, which are independent, right? Now this equation 4 satisfies one need, that it does not contain the Fi, small fi, that is force of constraints, but it deals only with statics. There is no time in this equation. We want a condition involving the general motion of the system. I mean to say, this equation 4 talks of statics. You cannot use this condition for the motion of the system because there is no time in it. Now what we do, we transform this, and what we do in that, we use the idea taught by James Bernoulli and developed by D'Alembert. Let us use that. For ith particle, we can write the equation of motion. The equation of motion for ith particle can be written as Fi is equal to Pi dot, where dot denotes the time derivative. It is simply Newton's second law. Force on ith particle is the time derivative of its linear momentum. We can write it this way: Fi minus Pi dot is equal to 0. Let me write it clearly. Fy minus Pi dot is equal to 0. What it says basically, it says that the particles in the system will be in equilibrium under a force equal to the actual force plus a reverse effective force minus Pi dot. Let me write it first. This minus Pi dot is called the reversed effective force. Of course, it is on ith particle in the system. Minus Pi dot is called the reversed effective force on ith particle. So we can say that the particles in the system will be in equilibrium under a force equal to the actual force, that is Fi, plus a reversed effective force minus Pi dot. That means the condition of equilibrium has been now reformulated. This has been done by James Bernoulli. Let me change here color. James Bernoulli and developed by D. Ellenberg. So one way of saying that the system is in equilibrium, you say the force, total force on each particle must be zero. That is Fi is zero. Another way of saying the same thing is we can say the system of particles is in equilibrium under a force not equal zero, but under a force equal to the actual force plus a reverse effective force minus Pi dot. Right? Now, if we use this in equation 1, we can write using in equation 1, we get this summation I Fi minus Pi dot with the virtual displacement delta Ri equal to 0 and emit 5. What we have done, we have replaced Fi in equation 1 by Fi minus Pi dot, right? We got this. Now see what we have done. Equation 1 is the condition for equilibrium of a system in terms of the virtual work, right? In which Fi is the total force. Equation 5 is also the condition for equilibrium of a system, but here we have replaced actual force by the sum of two forces, Fi and minus Pi dot. Plus point is equation 5 contains time derivative of Pi. So it can be used to study the evolution of the system. It can be used to study the motion of the system. Now in equation 5, again we resolve this total force into applied forces and forces of constraint. Let me write that. Again, resolving